All right, so today we're going to talk about heating and cooling curves. Heating and cooling curves. This, you guys, is in chapter 17 in your textbook, and it's section 3. But when you read section 3, please ignore all the calculations, because at this point in the States of Matter chapter or unit, we're just only covering concepts. So the math will do it later when we get to it. All right, so you have here something. So that's the heating curve of water. So heating curve of water. And so it looks something like this. And then something like that. And something like this and this. And here's my question to you. How many steps are there for a piece of ice at negative 10 degrees Celsius to reach 115 degrees Celsius? So that's my question. So you have here your piece of ice. Let me use another color. So here I have my piece of ice at negative 10 degrees Celsius. And this is 0 degrees Celsius. And this is 100 degrees Celsius. And I'm going to assume that this is 115. Might not be to scale, but that's okay. And that's 115 degrees Celsius. Obviously, that means that this is the temperature over here, and the unit is in degrees Celsius. And basically, this is time. So what happens over time? And we're not even putting a scale to it. It's not important. All right. So looking at this, so at negative 10 degrees Celsius, what do we have? What state of matter do we have? Well, we have a solid, right? And then this solid is going to increase in temperature until it reaches 0 degrees Celsius. So you have ice here. So that's I'm going to label this my first step. And then, so this is my solid. And then what's going to happen at 0 degrees Celsius, you guys? Well, what's going to happen at 0 degrees Celsius is what we call melting. So melting is going to occur over here. When you are melting, you see we have a plateau, right? So this plateau simply means that the temperature does not change. But what is it that changes when you have this plateau here at 0 degrees Celsius? What changes is the state of matter. If you actually bring in a piece of some ice and mix it with water and get a thermometer, use a thermometer, you will realize that the temperature will stay at 0 degrees Celsius until all the ice has melted. And that's assuming that you are at room temperature. So if you're at room temperature, obviously, the ice and water mix is going to stay as is until all the ice has melted. So you have no temperature change, and you have actually both states of matter coexist together. So you'll have a solid and a liquid. And this is my second step. And now looking here, what happens here? What's going on here? Well, the temperature goes up from 0 Celsius to 100 degrees Celsius. So there's a temperature increase. And this temperature increase, you guys, is my third step. What's the state of matter during that increase? Well, you're going from 0 Celsius to 100 degrees Celsius. If it's water, you know that between 0 and 100, we have a liquid. Okay? Let me go back to this plateau here. At that point right here, all my ice has reached 0 degrees Celsius but has not started melting yet. At that point, all my ice has melted and you have nothing but liquid, and then the temperature goes up. Okay? So when I reach here, I have liquid at what temperature? At 100 degrees Celsius. Okay? And then I have another plateau. So this, I have some liquid here, but I have another plateau here. What does this plateau mean? Well, at that point, I'm at 100 degrees Celsius. What do we know happens to water at 100 degrees Celsius? Well, it boils, okay? So you have water plus gas, and this combination, these two states of matter are going to coexist or stay together at the same time for as long as, so at 100 degrees, that's the boiling temperature, for as long as not all my liquid has turned into a gas. The minute all my liquid has turned into a gas, you're right here, okay? All my liquid has turned to a gas that has a temperature of 100 degrees Celsius, and then we're going to have, if the temperature keeps going up, the temperature of the gas is also going to go up, okay? So this is my step number 4, and this is my step number 5. So I believe this answers this question here, which is how many steps are there in a piece of ice for a piece of ice at negative 20 degrees Celsius to reach 115 degrees Celsius. Okay, so we answered the question really, and the answer is 5 steps. Okay, so this is just the general idea. Here I forgot to mention that over here, what happens? We call this melting. This area here, that's when you have your ice melt. This is when you have your water boil, and we call this vaporization. Okay, so that's the boiling. We call this vaporization. All right, so let's analyze every single step. So we're gonna go ahead and analyze step number 1, you guys. So what happens in step number 1? With step number 1, the temperature goes up, right? So temperature goes up from negative 10 degrees Celsius to 0 degrees Celsius. And so basically the temperature goes up. Okay? So there's a temperature increase. Okay. So that's in terms of what happens to the temperature. All right. But you also have one state of matter that is the solid state of matter. And why am I writing all these details? You'll see in a minute. Solid. Solid state of matter. Solid state of matter. And in terms of energy, what happens? Well, if the temperature is going up, that means that what is being absorbed? If the temperature goes up, it means that kinetic energy is being absorbed. There's energy absorbed. And it's kinetic because kinetic energy is proportional to the temperature. So when the temperature goes up, the kinetic energy goes up. So when T goes up, it means that the kinetic energy goes up. And since we have an increase in temperature, we know that we also have an increase in kinetic energy. What is this energy used for? Well, this energy is used for breaking down the intermolecular forces a little bit. So the temperature increase here, it brings the temperature from negative 10 degrees Celsius to 0 Celsius. So it's warming up my ice, okay? So what I can say here that kinetic energy is absorbed. So kinetic energy. And from now on, I'm going to use just KE, short for kinetic energy, is absorbed from surrounding to increase the temperature of ice. Okay? So this is the first step. Temperature goes up, the temperature increases, you have one state of matter, kinetic energy is absorbed from the surrounding to increase the temperature of ice. Now, what's going on in step number 2? Well, in step number 2, you have something different. You have a plateau. So the temperature remains constant. So basically what happens is that the energy is absorbed from the surrounding to do something else other than increase the temperature. It is used to loosen the intermolecular forces between the solid particles to allow it to melt into a liquid phase. So the energy here is absorbed from the surrounding for a different purpose. It's not to increase the temperature or temperature change, but this is for the change in the state of matter. So this energy that is being absorbed is now not kinetic energy, since the temperature stays constant, but it is potential energy. So let's write that down, you guys. So in this state here, or in this step, it's very important to note that temperature remains constant. Very important. And what else? Well, there is a phase change, obviously from solid to liquid. Okay? Energy is still absorbed, but the purpose of the energy being absorbed is different. It's not to increase the temperature this time, but it's used to loosen the intermolecular forces between the solid particles. Okay, so to loosen and I'm not going to write intermolecular forces, I'm going to write short IMF. You should know that IMF is intermolecular forces right now. Okay, to allow solid to melt into a liquid. And again, since the energy absorbed does not help increasing the temperature, we know that the kind of energy that is being absorbed is potential energy. So potential energy is absorbed. Okay? All right. Now, step 3 is very similar to what step, you guys? Well, what do you see in step 3? Again, you see an increase in temperature, something similar to what you have seen in step 1. So step 1 and 3 are very similar in that sense. All right. So here the temperature goes up again, but this time it's the temperature of the the liquid that is going up. We know the temperature increases. We know we have a state of matter that is liquid, and the kinetic energy is absorbed from surrounding to increase the temperature of the liquid. So it's very similar to step 1, except that the state of matter is different, the temperatures are different, but it's really the same idea. So, to explain that, you know that temperature goes up from 0 degrees Celsius to 100 degrees Celsius, and that the temperature, well, obviously that means that the temperature increases. We have a temperature increase. we have a liquid state of matter, right? Liquid state of matter. And we know that kinetic energy is absorbed from surrounding to do what? To increase the temperature. To increase temperature of the liquid. Now I want you to notice something. By now, hopefully you have noticed it. We cannot have both at the same time. An increase in temperature and a change in the state of matter. You always either have an increase in temperature or a change in the state of matter. As I mentioned, if you look at the plateau here, right here, means that the melting occurs at 0 degrees Celsius, so no temperature change. Now, when the temperature changes, you know that you have one single state of matter. So you cannot by any means have a change in the state of matter and a change in temperature at the same time. These two cannot happen at the same time. Energy is being absorbed either to increase or change the temperature of my substance, or it is used to change the state of matter, but never ever both at the same time. This is something very important to remember. So basically, step 4, we're right here, we're doing vaporization. That's our second plateau, which is really going to be similar to our step number 2, except that we're going to change some of the wording here. And so this is copy, paste, and let's see, what is it that we are going to change? What is the vocabulary that we use, that we're going to use in step 4 that's going to be different from step 2? Well, the temperature remains constant. So let's look at that. Does the temperature remain constant in step 4? Well, yeah, it does. We are at 100 degrees Celsius. Okay, good. There is a phase change from solid to liquid. Is it from solid to liquid now? Well, no, it is from liquid to gas. So we're going to go ahead and change that. So that's one thing we're going to change. So there is a phase change from liquid to gas. Energy is absorbed from the surrounding. Is energy absorbed from the surrounding? Well, yeah, because you are going to break down the intermolecular forces to go from liquid to gas, because you know that gas is a state of matter that's way less compact than the liquid. So you need to break down, not loosen the intermolecular forces like with melting, but you need to break them up completely. So there is a difference a little bit here. So it says there is a phase change from liquid to gas. Energy is absorbed from surrounding to loosen the IMF to allow the solid to melt into a liquid. Are we going to loosen the intermolecular forces? No, we are actually going to completely break down the intermolecular forces. So energy is absorbed from surrounding to completely break down the intermolecular forces to allow, what now? To allow liquid to allow a liquid to boil into a gas, to allow liquid to boil. Oh, I didn't need to squeeze the words that much. To allow liquid to boil into a, what now? A gas. Potential energy is being absorbed. And it's true, because I don't have a temperature change. The temperature is constant. So in that case, the energy that is absorbed is in the form of potential energy. Okay. And our last step is step number 5, And that's when the temperature goes up from 100 to 115. Okay, so step 5, and that's so I can do the same thing, and I can cut and paste to make it easy and just change the words, and it's like an exercise for you guys. You can just do that like an exercise. So in this step 5 here, what's going on? Temperature goes up from, well, not from 0 to 100, but from 100 to 115. That's how I know, but just by looking at that question over here and by looking also over here. Okay, so so temperature goes up from 100 degrees Celsius to 115 degrees Celsius. Temperature increases. And do we have a liquid state of matter now? Well, not really. What do we have? What state of matter now do we have? Well, it says, oh, I didn't even write it, so I'm going to go ahead and write it here. This is a gas state of matter. Now that's beyond or past the boiling point, so it's a gas state of matter. Okay, so we're just going to change that and write down gas state of matter. Okay, so gas state of matter. Kinetic energy is absorbed from surrounding to increase the temperature of the gas. Okay, so basically something like that has 5 steps to it. Now let's say that I have a piece of ice that we start, let me use another color, that we start over here at -10. I have a piece of ice that I want to put on my table in the kitchen and a plate or a container, and I want it to reach the room temperature. How many steps is that? Well, the ice has to go up to 0 degrees Celsius, and then it's going to start melting, so that's my second step. So I have 1, 2, and then it's going to warm up all the way until it reaches room temperature. So that, in that given example, that's a 3-step question or 3-step problem. Okay, so it really depends on what the question is asking. I could ask you, for example, if I do something differently, what happens if I have a piece of ice at -10 degrees Celsius that I want to bring to a liquid at 0 degrees Celsius? So liquid is here, but at 0 degrees Celsius, we're over here. So that's 2 steps, okay? So it really depends on the problem, what the problem is asking. I could have up to 5 steps. That's the maximum number of steps I can have. But you can have 1 step, 2, 3, 4, or 5, okay? So that's the heating and the cooling curve. Now, we can do something else. I can just show you something a little bit different. I can show you this. I can now show you something that looks like that. Okay, so this would be the opposite of this, right? So that is actually what we call, because this is temperature, so what's going on at the temperature as time goes on? What's going on? Well, the temperature is going down, right? So that is not a heating curve, but it is a cooling curve, okay? So, and it would be also the cooling curve of water. So you get here, we're at 100 degrees Celsius. And let's say we're still at the same 115 from the previous problem here. And then over here, oops, so I'm going to have to go up a little bit. So this is 0 degrees Celsius, and this is my famous 10 degrees Celsius, right? So this is cooling though. So here you have the same 5 steps, but the opposite way. You're going to go from 115 to 100 degrees Celsius, right? So this is a gas, And then here, you're going to get your condensation over here in that plateau here, going from gas to liquid, right? Gas plus liquid. And here, that's your third step. So this is, if I'm starting up here, that's my first step. This is my second step. And over here, that's my third step with what state of matter? I have a liquid. And over here, what do I have? Well, I have my freezing, right? So that would be liquid plus solid, and that would be my step number 4. And then step 5, that's when my ice goes from 0 to -10. So if you look up here, is heat, if you look on this curve here, the heating curve, is heat absorbed or released? Well, we've been saying that heat is absorbed. We've been saying that heat is absorbed. Regardless of what step you're in, heat is always being absorbed. It could be kinetic energy, it could be potential energy, but heat is always absorbed. So when heat is absorbed, we call this an endotherm. So heat is absorbed. So this is what we call an endothermic process. Endothermic. And it's, by the way, one word. So let me just write it like that. Endothermic, thermic process. Endo means in, and thermal, heat. So heat is taken in or heat is being absorbed. Okay? So that's heat. When we're doing cooling, though, heat is not being absorbed, but heat is being, well, the opposite of absorbed is released. So we say when you have a cooling curve, I don't need energy to put the intermolecular forces together. The opposite is true. When you put the intermolecular forces together, you don't need energy. Energy is being released. That energy that was prior absorbed to break them down now is being released when you put them back together. So the cooling curve here, it is an this is when heat is released, and we call this an exothermic process. Exo means exit or leave. Okay, and thermic again, heat. So heat is leaving or heat is being released. Okay, so it's very important to understand that heating is absorbed and that cooling is being released. You can actually do an exercise and try to describe each and every one of these steps, just like what we did up there in with the heating curve. You can absolutely do that. Okay, so that would be a great exercise for you to do. All right. Also, I want to ask you one thing. Oh, I want to tell you one thing. Okay, so when we go from solid to liquid, or we're going from liquid to gas, this process, solid to liquid, is what? That's melting, right? When you go from liquid to gas, that's vaporization, right? These two processes, they need heat to be absorbed. So melting and vaporizing, they are both what? Endothermic. These are endothermic. When I look at a cooling curve, what's going on? Well, what's going on here? What am I doing over here? Well, I'm going from gas to liquid. That's not vaporization anymore. That's the opposite. That is condensation. Okay? What's going on over here? Well, I'm going from liquid to solid. That's not melting anymore, but it's freezing. So in these two processes, heat is being released. So I can say, so gas to liquid, that's condensation. And then a liquid to solid, that's freezing. And I can say that condensation and freezing are both exothermic processes. Okay? All right. One more thing that I want to bring to your attention before we do a comparison between the heating cooling curve and phase diagram is that I want you to look here at, and I'm going to use another color. I want you to look at the plateau that's over here and the plateau that's over here. So I have melting and vaporization. When you're melting, what are you doing? When you're melting, you're loosening the intermolecular forces, right? When you are vaporizing, what are you doing? You're completely breaking down the intermolecular forces. Which one do you think requires more energy? To loosen the intermolecular forces or to completely break them down? Well, in reality, breaking the intermolecular forces completely down requires a lot more energy than melting over here. So that's why, and I purposely did that, the plateau for the melting over here is a lot smaller than the plateau for the vaporization over here. We call this, the amount of heat needed to vaporize a substance is called heat of vaporization. So again, the amount of heat needed to boil a substance is called heat of vaporization. And then the amount of heat needed to melt a substance is called heat of fusion. Sorry, it's not called heat of melting. It would have been easy, but it's called heat of fusion. And because you require more energy to break down all the intermolecular forces, to break down completely all the intermolecular forces, you require more energy than loosening it, we can say that the heat of vaporization is greater than the heat of fusion. And this is true for any substance. You need more energy to break down all the intermolecular forces versus just loosening them. That's why the plateau here for the melting is not as big as the one for vaporization. Okay? All right, so with that said, I just want to go back to the phase diagram, say something about it, and compare it a little bit to the heating cooling curve. Okay, so let me just draw a phase diagram. And I'm going to go ahead and draw the phase diagram of water. And you should right away recognize that it's the phase diagram of water. So this is P, T. How do you recognize that it's the phase diagram of water? Because, of course, of the negative slope that I drew here. And this is a solid, this is liquid, and this is gas. And this is my triple point. Okay, and then when I am, let's say this is 1 atm. Okay, and that I am over here. So 1 atm. So I forgot to mention that this is the phase. Always have to title any graph you plot. It has to have a title. Phase diagram of H2O. And let's say I'm over here and I'm over here. Okay. So basically what's going on here, I am at 1 atm, so really what I have here in the middle, since this is the phase diagram of water, and I'm at 1 atm, so this is between solid and liquid, so what is that? What's the temperature here? What's the temperature of water when I am at 1 atm between solid and liquid? That is 0 degrees Celsius. And here, that's really the boiling point temperature of the water. And you see that you have between the 0 and the 100, you have this line here, the straight line. This is when I have my liquid water. This is when I have my water vapor. Over here, my water vapor. And over here, I have ice. Okay? Ice, and here I'm going to call it steam. That's because it's water. Okay? So when you look at that, you know from the heating and cooling curve that at that point you have the liquid and the solid coexist together, and you know that you have at that point the gas and the liquid coexist together. What I forgot to mention in my previous video is that on any point on this line right here, you have both state of matter coexist. You have the solid and the gas here. Any point, so you'll have any given combination of temperature and pressure on this line, you have both states of matter coexist together. Okay, same thing here. So if you look here, I'm gonna go ahead and use another color. If you are here, okay, at any point on this line, any combination of this temperature here and this pressure, you have both a state of matter coexist. You'll have a liquid and a gas, or at any point on this line. So let me use another color. Let's say I use this. So at any point on this line, both states of matter coexist. That's why when I look at this point here and at this point here, I know that solid and liquid coexist together. And I gave you the example earlier of getting some ice and put it in a container that has water and get a thermometer. As long as you have both states of matter, it will remain at 0 degrees Celsius, okay? And you are at atmospheric pressure, which is 1 atm. You look here, water will not boil until water will continue boiling at 100 degrees Celsius until you have nothing but steam. So anywhere on the line, depending on which two states of matter you're in between, you'll have both states of matter coexist. Just like when you're over here, right in the middle at the triple point, you have the three states of matter coexist together. All right, so basically in a heating or cooling curve, what you see is just that one line that is over here, this area over here. If you are increasing the temperature, this way you're heating, and that's going to look like a heating curve. If you are decreasing the temperature, it's going to look like our second diagram, the one that you have right on top of this one here, on top of this phase diagram, and that's when you're cooling down, okay? But you see that point and that point over here, these 2 points over here, are represented by the plateaus that you see in your heating and cooling curves. So these plateaus represent the points that you see on your phase diagram. So they correspond to these 2 points over here. Okay. I think at that point I am done. So just let me know if you have any questions. Okay.